Hello, I'm Courtney Carr, the Director of Marketing and Education for CAPSA. Thank you for joining today's Introduction to Centrifugal Casting presented by Alistair Brixley and Doug Smith from Bunting Bearings, LLC. Alistair is the Executive Vice President of Sales and Marketing for Bunting Bearings, and Doug is the Vice President of Sales for Bunting. Both are located in Holland, Ohio. During the presentation, you may submit questions into the Questions tab on your webinar toolbar, and we will answer them at the conclusion of this presentation. Following the webinar, you will receive a link to a survey. Once you complete the survey, there will be a link to download the presentation slides. You will also receive a recording of today's webinar. Please feel free to share the recording and slides with others in your office. With that, I would now like to turn the presentation over to Alistair and Doug.
Hello, everybody. This is Doug Smith, VP of Sales at Bunting Bearings, and Alistair Brixley, Executive Vice President. Thank you for taking the time today. Bunting Bearings and CAPSA would like to thank you and welcome the participants for taking time out of your day, and I know you've all got busy schedules. We are planning to provide you with an introduction to centrifugal casting. Our intent is to cover the subject in a relatively general manner so that you'll walk away with some insight to what we do and what centrifugal castings are in the industry. Okay, the webinar we're providing is to give you the basics to enable you to have a general understanding of how to go out and hopefully obtain inquiries for centrifugal castings. They say the centrifugal casting technique was developed by Mr. Eckhardt in England. That by no means, although he was English, that by no means mean that I'm an expert in the field of centrifugal casting. So, starting it off, in short, what is centrifugal casting? In simple, true centrifugal castings is a casting process in which a foundry pours a specific molten alloy into a spinning permanent die, allows it to cool to desired geometry, and then extracts the casting from the die. It's really pretty simple, you might think. Spinning is really the differentiating characteristic that sets this particular process apart from other casting techniques like continuous cast, permanent mold, sand cast, or others. Yeah, sounds pretty easy really, but not really. The main specification for copper industries for centrifugal castings is B271. In the bronze casting world, it is important to specify the casting method if it's critical to the end user or application, as there are subtle differences in the physical and mechanical characteristics between the various cast methods. Other common bronze cast methods are dictated by other ASTMs such as ASTM B505, B148, B806. Many of our people listening to this webinar are pretty familiar with most of the ASTM methods. But to reiterate, it's really important to make sure that you and your clients understand what cast method they want. Too many times people ask for a very generic ASTM, and most times that's okay, but there's always a time here or there that it matters what ASTM they want to cast to. So again, what is centrifugal casting? Centrifugal casting is one of the more common casting techniques used to produce both ferrous and non-ferrous alloys into a specific shape. Generally speaking, the casting geometry is typically hollow and cylindrical in nature, but it can be used to produce non-cylindrical shapes with the implementation of special dies or particular casting machines and other various techniques. Typically, bunting produces mostly cylindrical in nature parts. There are three basic types of centrifugal casting. They're primarily defined by the axis upon which the die spins. There's the horizontal, the vertical, and inclined. But the two most common processes are horizontal and vertical. Centrifugal forces are utilized to distribute molten metal into a mold cavity, resulting in a great amount of pressure being exerted on the metal. Due to the forces at work, the lighter impurities are forced to the inner diameter, where they can be machined off, which results in a better quality metal casting. One of the other primary issues is because of directional solidification that occurs in this type of casting, there's typically an enhanced or more uniform grain structure along with mechanicals that are very similar to forgings. densities can even be higher than sand castings in some circumstances. So directional fluidification, in simple terms, is basically when you pour the metal, it begins to cool from the outside and works inwards. So we can help control the cooling cycle, grain structure, and other pieces of the puzzle. So I thought it'd be kind of interesting. I've been in the industry about 13 years, and I've often heard what we do pronounced differently. So I did a little homework. So how do you pronounce centrifugal? Well, I'm clearly from America. My counterpart here is clearly not American speaking, but British speaking. So if you look at the chart there, centrifugal is how we Americans say it, and I'll let Alistair pronounce how he would say it.
Yeah, and in Britain we pronounce it centrifugal.
It's kind of like the aluminum and aluminium. So just for anybody that wondered, that's the story.
You may hear me switch between the two when I forget that I'm talking to Americans. So it's centrifugal or centrifugal, both are correct.
So why would you use centrifugal castings? There are a number of reasons for it. Centrifugal castings are typically used when an application desires the physical or mechanical attributes of the process. Keep in mind that the mechanical attributes of all the different ASTMs have different resulting minimums and maximums. So again, going back to, you need to specify the ASTM that a customer wants. An alloy is not readily available as a standard industry stock size or alloy. Pick a very uncommon alloy in bronze, and chances are it's not sitting on the shelf somewhere, so we can make it in centrifugal due to a die and smaller furnace requirements. A small amount of a non-typical alloy, similar to what I said above. Large sizes that can be made by other cast methods are needed. So if you need a really large piece of bronze, let's just say you need a 40-inch diameter piece of bronze, you're not going to find that in most of the other alloys, at least not for the mechanicals that you want. So it's a great opportunity to do larger parts. Also, a centrifugal casting can achieve a more near net shape, thus reducing the metal and machining costs. So we can spin this with a fixed OD and drive it into the middle. Again, we tend to do more cylindrical, but some of the people in the industry will actually centrifugally cast more to the near net geometry shape as well. For instance, a flanged die.
As I said before, there's 3 different types of centrifugal casting. The 2 most common are vertical and horizontal. Vertical centrifugal castings normally have a larger outside diameter than a shorter length ratio. They can also be used to make non-cylindrical shapes. Horizontal centrifugal castings normally have a greater length than the outside diameter. As such, this cast method is better suited for longer proportion parts. All 3 methods can be used to cast ferrous and non-ferrous alloys. At Bunting, we don't use the inclined method, but it's a matter of choice. Sometimes it's used by other companies when they're producing tapered castings.
So some general notes on alloys. Not all alloys are equal when it comes to producing centrifugal castings, as each alloy has its own set of characteristics, kind of like your kids. They're all a little differently. In general, we can cast most of the bronze alloys that are commonly used in the industry. ODs can be as large as 100 inches or more. Those are very specific requirements, and certain vendors have that kind of capability. IDs can be as small as 2 to 3 inches. Again, there's a lot of rules that apply to achieve these different things. So those are very general statements. There are many factors that can limit the capabilities of any one casting operation, i.e., casting size, the casting machine itself, the weight of the casting and what the furnace can provide, the speed that we run the die, the alloy itself, the die itself. Remember, in this industry, the die fixes certain attributes, furnace size, chemistries, and there's just all kinds of different things that come into play here.
So what are the main advantages of centrifugal casting? These are the main ones: reduced internal porosity, consistent chemical composition, enhanced grain structure. That's one of the main ones. Size of the casting. Most people can only do continuous casting diameters up to 16 inch, but as we said before, you can go up to 100 inches plus on a centrifugal casting. Flanged or step casting, which again, of course, you can't do on continuous cast. Low volumes. If you want a one-off item, we can produce a one-off item. It's also cost-effective for non-standard alloy options, where for continuous cast you would need round about 2,500 pounds run to make it economically viable, but you can do a one-off centrifugal casting. High and more uniform mechanical properties. The dies are reusable, so if you want a one-off part, but you want that every other year or every year, the dies are reusable. You don't have to buy a new die every year. And as we said before, you have a very dense pressure-tight casting.
Disadvantages, at least for us, primarily tubes only, cylindrical in shape, no solids and plates. Again, there are some very unique centrifugal casters that have other abilities, but in general, typically speaking, no solids or plates. Downside is high stock removal. Compared to a continuous cast where you've got roughly 100,000 in your directions of nominal cleanup, in the centrifugal, depending if it's vertical or horizontal, you tend to have more cleanup stock to get down to your stock to finish tube size. So there are some negatives to that respect. Requires semi-finishing, and typically bunting and most of the industry does not sell centrifugal castings in a raw state. Primarily speaking, we want to semi-finish it to make sure we've got good solid metal, and then also you don't want to pay for more metal than you need. So our industry typically sells this as a semi-finished blank. Higher costs for larger volumes where continuous cast is acceptable when available. So it can be more expensive than continuous cast if you're making something simple with an IDOD. Limitation of dies. Remember, the die is a central part of making a centrifugal. So if I don't have the right die or your supplier doesn't have the right die, it can be more expensive than it should be. So there are limitations there.
Okay, so what we do first is we melt chips or ingot or a mixture of both in one of our induction furnaces, and then the metal is poured into a large ladle, which is then taken to the centrifugal caster. Once the metal has been poured in, any slag that is on the top is then skimmed off the top to leave the pure molten metal.
So if you notice the picture on the left, we've got the ladle being poured into from the furnace. On the right, that's another view of similar process. So the furnace, which is typically around 3,000 pound loading, will load into the ladle. And that defines the amount of weight that you can pour into the centrifugal. So that is one of the limiting factors when pouring a centrifugal, is how large your ladle is.
And at this point, also the chemistry of the metal is checked to make sure it's within the CDA specification.
Centrifugal die, that's obviously what we're using to make these castings. Centrifugal castings are produced in steel or graphite. It just depends. There's different reasons why we go different ways. The dies produce the outside and the length dimension of the casting. Again, the ID of the mold establishes the OD of the casting, and the same with the length. So in order to determine the ID, it's a matter of how much metal you pour into that die. So the OD is fixed, the length is fixed, and the ID is proportionate to how much metal you pour into it. Mold preparation. We clearly have a die that we're going to use. Keep in mind we're pouring in very hot molten metal into either graphite or metal die. So one of the things we need to do is make sure that the metal, the bronze in this case, doesn't stick to the die. So the walls of the centrifugal mold are first coated with a refractory ceramic coating, which is carried out in basically 4 steps. We apply it, we rotate it, it dries, and then we bake it so it's hot. So you see the whites in that picture, that's the refractory on top of the steel in this case. So the mold is then preheated for casting. So the mold is rotated, keeps it warm, and in that process, we start to calculate, or it's already been predetermined how fast we're going to run that mold to produce the next casting. And we'll talk about that next slide.
Okay, prepping to pour. 2 sizes are controlled by the die. That's the outside diameter and the length. We calculate the pounds of metal required to give us the required ID. The weight calculation of the alloy also includes the amount of metal that needs to be machined off. The die temp is important, as well as the pouring spout and then the ladle temperature. Everything has to be kept at the perfect temperature so that the metal pours into the die evenly. when we're also pouring into the mold to produce the casting, at the end we can also produce a coupon, and this coupon is used for people who require a chemical or physical testing afterwards.
To give a little more information, or at least a more visual on what's happening, if you'll notice on the left picture there, it's what we call heating the pouring spout. That's essentially, as you can tell by the right picture, where we pour from the ladle into the spout. The spout's basically a holding area for metal as it flows through the spout and into the mold. And in this case, this is a horizontal die. If it were a vertical die, it would come straight through the top. But in this case, it's basically a reservoir material that allows it to flow uniformly into the mold itself. But again, it really comes down to having all the right temperatures and the right chemistries. And the person pouring metal really worked hard to make sure he's pouring in a very specific way, keeping it uniform and consistent. When the mold is rotating, it applies high centrifugal forces. Again, in our world, we talk about the G's. We talk RPM and the resulting G's, G force. So as the result, the less dense materials and impurities are driven to the inside of the diameter of the casting. So if you can envision material being poured into this die, spinning at a very high rate, as it's in there spinning at that high rate, the lighter impurities tend to stay to the inside of the casting. So a lot of times, if you look at a casting after it's been cast, the ID is not as visually pleasing as the OD typically. Typically speaking, centrifugal forces range from 40 Gs to 100 Gs from the cast inside diameter. That's where we tend to do our calculation from. And again, horizontal is generally runs faster than a vertical casting, again, because of the vertical nature versus horizontal nature. As metal solidifies directionally under pressure from the outside to the inside, the castings will have a defect structure, excuse me, without porosity or gas pockets. That's obviously the goal. I will tell you that's not 100%, and that's why we semi-finish these things from occasion. It is not always a perfect science, but you know, if we follow the rules, generally speaking, we make some really good alloy. This is an example of one of our smaller vertical centrifugal molding machines, I should say. As you can see, they're pouring this now into the top center of the mold versus the picture we saw a couple of slides ago that were poured on the side of the mold. Again, this is one of our smaller casters. We do have different casters. We have very large casters to very small casters. They differentiate by speed. They differentiate by size and weight loads, by what type of mold it'll hold. There's a lot of different variables that come into play. This picture is an example of, again, one of the smaller vertical casting machines. You can see the die in the inside, and then you can see the lid on the upper right-hand corner. When that gets all put together, it's poured through a lid. This is another example of a smaller horizontal casting machine. You can see the pouring spout there. Again, this is a smaller machine than we saw a few slides back, but again, it's conceptually wise, it's the same idea.
So once the metal has been poured into the die, it has to be cooled with or without water. It's important because depending on how much water and when you put the water on, if you cool the metal too quickly, you can sometimes trap the impurities which you want to reach the ID. But cooling begins quickly at the mold wall and proceeds inwards, and is sometimes helped, as I said before, by water being sprayed directly onto the outside of the die. Also, with the cooling, using cooling or not using cooling depends on the type of alloy that you're casting. So the next picture here shows you how we extract the cast from the mold. The casting shrinks away from the die wall, allowing the casting to be removed safely. These show you here, these are centrifugal castings, smaller ones, and you can see that the impurities on the ID and the OD is pretty smooth, but we still machine the OD to prove that the high integrity of the material. On the left, you can see a vertical casting, and this shows more how the impurities have all gone to the inside diameter, which we machine off. On the right-hand side, it shows the smaller OD, longer castings, The white residue on the outside of the casting is where the mold wash has actually baked on to the bronze material.
So we've kind of walked through the process of melting the material, checking chemistries, preparing the die, pouring into the die, making the casting, cooling, extracting the die, and then afterwards we take that casting as is, we call it an as cast, to the machining area where we then semi-finish it. As I said earlier, it's not common in our industry to ship an as cast casting for fear of finding a porosity or some issue along that line, and also the clients don't want to pay for extra material they don't need. So this is just a pictorial of a casting on a machine being semi-finished down. Typically speaking, one or two ways. People will give us a particular set of dimensions they wanted to. Other people will give us a stock to finish to dimension. Again, that's always something that we try to ask clients, and as a buyer, you should always try to be very specific in what you want. This is a good example. This was a 932 cast alloy. It was requested as a stock to finish to 23 inches by 31 by 13. It was vertically cast. That wasn't specified, but because it's now getting larger in OD, typically it goes to vertical. Typically speaking, you'll find the larger castings are generally going to be vertically cast. And then again, this particular alloy required a full certified ASTM, both chem and fizz. So you'll notice the writings on the information there. We've got a part number, we've got a stock to finish to dimension, and then we have the actual dimensions. Again, typically speaking, most people want about 1/8 of an inch of material, nominal wall stock, to clean up to. And those are the actual dimensions that our machinists actually write on there, confirm that it's where it's at. You can also see where there's the heat designation on there, so we have traceability. And then also there's a sales order, an internal number. But that is a pretty common thing you'll see from us. But again, I want to stress it's important for people to make sure you're clear on what you need, because there are a lot of misunderstandings in the industry. People will ask for something and mean something else. So one of the biggest things we can do as an industry is make sure we're really clear on method, alloy, dimensions, things like that, that at the end of the day, you'd sure hate to make a 31-inch diameter casting and find out that you made it, 100 thousandths too small. That's never a good day. Here's an example of another centrifugal part that is machined at this point. But again, it's a pretty large centrifugal finished part. Again, here's another centrifugal standard sleeve bearing, but pretty large. You can see how big that mic is compared to the casting, and just a good example of another casting. And then finally, here's another sample of a flanged die, flanged casting finished. In this case, we make this part using a flanged die so that we don't have a lot of excess material, and it makes for a more competitive part for the client.
Okay, to recap on materials, there's a wide range of materials are available, but just at bunting, we pour over 150 different alloys. The main alloys that we produce are tin bronze, leaded tin bronzes, aluminum bronze, and manganese bronzes. And in recent years, getting more and more popular are the lead-free bronzes. We're producing a lot of centrifugal castings in the eco bronze and in bismuth as well.
So hopefully you've spent 23-4 minutes here getting a feel for what centrifugal is. Many of you deal with it on a day-to-day basis. Hopefully this has given you some visual information for you to see how we're doing it, and a little understanding basics that we're doing. We could probably spend a whole day doing this in detail, but hopefully it's given you an idea of what it is and what our industry does, whether it's bunting or another centrifugal caster. It's a method that's been around a long time and without question has a real need in industry, and we have a lot of producers that make great products here in the United States. Alistair?
Yeah, for me, it's a basic introduction, so hopefully it allows you to go out and obtain inquiries for centrifugal castings, and hopefully you send them to bunting.
So I believe.
Thank you so much, even for that little plug at the end. As a reminder, please submit any questions using your webinar toolbar. And we have our first question. What's the longest casting that you can pour?
At the moment, for us, it's 60 inches.
Yep. But there are people in the industry that do as much as 100 inches that I'm aware of. But
at bunting, it's 60.
Right.
Next question.
Often, just on that subject, it is often defined by the weight of the casting as well.
Yeah.
All right, next question. Assuming that you have a die, what's the average turnaround time for a casting?
To make the casting and send it out the door?
I'm going to say yes. It wasn't specified.
Sorry.
Yes.
I need to just finish that. Yeah. So realistically, the industry from a lead time standpoint probably runs 3 to 8 weeks, depending on what time of the cycle or how busy the market is. As far as typically speaking in the industry, I'm guessing you're probably looking at 3 to 6 weeks to 8 weeks is probably normal in our industry, if that's what you're asking. As far as when we start making it, let's just call it it's a day to make the casting and it's a day to machine it. Roughly speaking.
Sometimes we do turn around castings in 48 hours.
Sure.
And we do have off-the-shelf castings already produced.
All right, well, that was the end of our questions. So thank you both again. As a reminder, for those of you who are attending, you will receive a survey about today's presentation. Once you complete the survey, on the second page, it says, thank you for completing it. There will be a link to download the presentation slides. In a separate email, you will also receive a recording of today's presentation. Okay, one more question, just in time. When mechanicals are required, do you spin a smaller tube?
Yes, we can go down to smaller sizes. We can go down to 2-inch inside diameter.
All right, if any additional questions come up, I'm sure Alistair and Doug will be happy to answer them. You can also send them to CAPSA staff, and we will pass them along. Thank you so much for attending. Have a great rest of your day.
Thanks, guys.
Thank you.
Ladies.